imagine Colby and Daisy have reasonable reasons they're not here as well. Let's go over the, Colby, Daisy, Tyler, and of course Zach, who I know about. Let's go over this quiz. So, question number 1. How do you place a positive charge on a metal sphere using a negatively charged rod? Which one? I know you didn't mark can't, so why'd you say that? The correct answer is A. I thought that was, I'm pretty sure you're the one who submitted this question.
No, that wasn't mine.
I think so.
I did something similar, but not that one.
Well, I had changed the wording.
Oh, that makes sense. Maybe.
Anyway, this was charging by induction, where you bring the charged object close and then you ground it, touching the finger is grounding. And what grounding does is it allows charge to move on or off as desired. So if I bring a negative rod close by and I touch it, the negative rod is going to push electrons away. And so the electrons are going to go onto my hand because it's a convenient place for them to go. Then I take my hand off and my metal is missing electrons, which gives it a positive charge. Number 2, a collection of various resistors are wired in series with a power supply. Which resistor uses the most power? The what? I still didn't hear you said.
Lowest.
Okay, she says the lowest resistance. What do they have the same if they're in series? The current. And because they have the same current, we want to look at how power relates to resistance and current. And power is always IV, the current times the voltage. Remember we talked about that. Voltage is the energy per charge. Current is the charge per second. And power is the energy per second that's being consumed. And so if they all have the same current, I'm going to take the V and replace it with Ohm's law. And power is I times IR, or I squared R. And so which one has the most power is going to be the one that has the most resistance. All right, third one. Doesn't sound like we are meeting with great success on this quiz. 2 long parallel wires have equal currents traveling in opposite directions. So I have one current like this and one current like this. What best describes the direction of force between them? That was from yesterday or Wednesday's lecture. What best describes it?
I was thinking attractive.
It's the other one.
I did a problem like this one too.
When they were parallel, then it was attractive. When they're opposite, it was repulsive. And finally, right, I sit there and let it randomize answers until I at least have more than 2, because like the first 3 times it had only 2 letters. Here we got 3, A, B, C. If light bulbs are connected in series to a power supply, which is the same again as part A, but now instead of asking for power, we're asking for current. So we already answered this with number 2. What can you tell me about the current if they're in series? All the same. Excellent. So current will be the same. I started at E and worked my way up. So there we have the answers to the quiz. Things that we've been studying in the last week. Now let's move to more fun things. Force of magnetism. Now we've already learned a little about the force of magnetism, right? We learned that magnets have poles that have been rather randomly named, the north-seeking pole and the south-seeking pole. And it turns out that just like with electric charge, opposites attract and likes repel. Well, if I have a wire with current through it, we learned that that current creates a magnetic field. That was what Ørsted noticed. Now today I have the stuff out so I can actually demonstrate this. Somebody want to come up and help me out? Okay, come on up, Denford. We'll have Denford help me out. Now, I will quickly try to remember how to adjust this so that's not it. Adjust it so you can actually see what we're doing. And yeah, I just remembered. So we'll be good in a second. So I'm going to actually take a video of this, and I'm going to have Denford be my videographer. So what you got to do is just sit here and hold this above. Yeah, just once works. Hold this above here so you're looking down at, yeah, just looking here. So we're looking at that. Now I'm going to take this wire, hold the wire here, and turn the power on. Clearly, the magnet responded, right? Ørsted, now his situation was probably more like this. If I put it down there lower, I'm farther away. What do you suppose is going to be happening if I put it farther away? Okay, slower. Why? Because the force isn't as big, because the magnetic field isn't as big, because we're farther away. Now, notice I had this running with the red on the same side as the red on my needle. And when I ran it, it rotated so red came toward me, which of course you can't tell which direction that is up there, but the red came toward the wires. So now I'm going to flip the wires so they're going the other direction. According to what we learned, what did that do to the magnetic field that's going to be created? Do what? It's going to change it, flip its direction. So now let's do it, and I'm going to actually lift it up so we have the bigger effect. And you see, indeed, the red now went away from the wire. What should happen if I put the wire so it is going like that? Okay, now there are two options. Either it does nothing, or it tries to flip it all the way around. So it depends on which way the current's going. Here, nothing, so let's try the other way. Okay, it's not very strong, but it moved it a little bit. I'm not going to play with that anymore. What I am going to do is still keep him here and say, since this is making a magnetic field, shift over here. Suppose I can pick these things up if I turn the current on with my wire. Okay? It's physics, right? We make ideas, then we test them, right? We come up with a hypothesis. Our hypothesis is, well, because there's a magnetic field created when a current goes through a wire, and because iron things are attracted to magnets, then if I put current through this wire, I expect I'll be able to lift it up. Let's test it. So you can see it's moving the compass, but it's not strong enough to pick anything up. Well, that's disappointing. But here I have a wire that I've done two things with. One is I've wrapped it in a whole bunch of loops. What does it do when I wrap it in loops? It condenses it. Because if you use your right-hand rule, on the inside, the magnetic field is pointing the same direction from each piece of wire as it loops around. So the magnetic field is much stronger when you make a loop like this. Second of all, I have this iron item in the middle. Now, we haven't studied that, but we do know that we have the little magnetic dipoles in the metal. And those little magnetic dipoles will rotate because of the torque when they're in a magnetic field. But when they do, it makes the magnetic field stronger. So using an iron core like this, you can make your magnetic field as much as 1,000 times stronger than it would have been without it. So now, a new hypothesis, okay, it wasn't strong enough before. Now, hopefully, I tried this beforehand to make sure it worked, and I got my iron a little magnetic already. So to pick up the lice thing, won't do anything at all to that one. This one here, it picks up a little, but won't take it off the table. Now let's turn it on. We see clearly, hey, well, it picks up these two things easily. Oh, sorry, yes, my videographer. Go ahead and go sideways on it so we can see them hanging. Yeah, picks them up easily. I just turned it off. You could see that the compass reacted when I turned it off, but they're still staying there. Why? Because I have reoriented the magnetic domains in the nail as well as in those things. So the paper clips are now magnetized as well. If we come back tomorrow, they won't be because they're magnetically soft. They'll realign. Instead of taking this out and doing the last demonstration, I'm going to shift. So I still need my videographer at work here. I'm going to shift to this bad boy. So what is this? Basically the same thing I was just playing with. Here we have all of the coils. And so that should make a magnetic field, right? I plug it straight into the wall and hope for the best. The worst, of course, is the lights go out. The best is, well, I'm just going to make it behave kind of like a magnet. Let's just take and put something on there. I've actually never done this. It's just, experiments. Making something that's magnetic, putting something that's ferromagnetic. Should be some kind of interaction. So let's plug it in for a moment. Was there an interaction? Why, yes! Clearly it did make some magnetism occur. Now one thing here is I'm plugging this into alternating current. Alternating current means that my current went one direction, making the magnetic field, let's say, come up in the middle, but then it shifted to the other direction, making the magnetic field go down. So the magnetic field was quickly shifting back and forth. And so that's why you heard this thing buzz some and get pulled in. Now I'm going to do something really cool. I'm going to put a little ring on top. If I put the ring on here, when the magnetic field changes, it's going to have an effect on the ring. So I'm going to start off with just the ring like this. And I plug it in. That wasn't exciting. When you're a physicist and your experiment is not exciting, what do? You make it exciting. That's where this comes in. This is a whole bunch of little iron rods that are insulated so I can't have electric currents flowing around in circles in them. I'm going to put this in here. What should that do to the strength of the magnetic field? Make it stronger. Makes it stronger means I can have more exciting things. So now let's try it. See, that was much, much more cool. What was going on? Well, I created a magnetic field, and this somehow responded to the magnetic field, had a loop. How can I make this respond to a magnetic field? What would I have to have in this to make it respond to a magnetic field? How can I make this behave like a magnet? Okay, have a current running around, so a charge moving through it. So somehow, when this had a changing magnetic field, it created a current in this loop. Now I'm going to change, by the way, this is not magnetic, right? It's not attracted to magnets, doesn't do anything with a magnet. So it had to have been that current. Change to brass, just to see what happens. What's different about brass? It is. It's copper and something? Yeah, I don't remember. It's a copper alloy. But it's a heavier metal. Clearly, aluminum versus the brass. This is heavier. But it's also a better conductor. So let's just see what happens. About the same thing. This here. What's different? It's aluminum. It's thin aluminum. Who cares that it's thin? What's different is it has the hole in it. So if it has a hole in it, you can't have current going around the loop because the loop's broken. You don't have a complete circuit. So let's see if that makes a difference. Okay, I'm going to rotate this so my videographer can see the gap there. And plug it in. Nothing. Put the aluminum ring around there and try it again. What was going on there? Because it wasn't a complete circuit, nothing happened here. So that's a way to test. Yeah, it had to be something to do with a complete circuit to make that occur. Now that ends my fun time. Thank you for being my own personal videographer. So back to what we had on the slide, there's definitely forces that will relate to either a current in a wire or to a moving charge, because what is a current? It's a moving charge. That's what Andrew had said. Now, these equations are actually, mathematically, they're what we call cross products. The force is only developed if you have the current perpendicular to the magnetic field, which is why I had things like the wire like this, so that it would make a magnetic field that went this direction and made a force that would, well, yeah, you need the current perpendicular to the magnetic field, or you need the velocity perpendicular. Other things to note on this, the current is proportional, or the force is proportional to the current, the length of the wire, and the strength of the magnetic field. Or it's proportional to the charge that's moving, the speed at which it's moving, and again, the strength of the magnetic field. But it has to be perpendicular. So now if you look in this picture, we show a wire. And in the wire, the current is going to the right. So the current's to the right, the magnetic field is up. Are those parallel or perpendicular? Perpendicular. That means we're going to have a force. Now, just to be clear, if the current was like this, I could break that up into a part that's perpendicular and a part that's parallel, and only that part would cause a force. So there would still be a force if it was neither parallel nor perpendicular, but it's only partial because part of the current would be perpendicular. Okay, so it's perpendicular. It shows a force direction. And here's how we get that force direction. We use what's called the right-hand rule, which is on the next slide, I think. The right-hand rule. So you take your right hand and you point your index finger parallel to, change color for this, current or velocity. And then you point your palm or middle finger parallel to the magnetic field. Come on, colors. And then your thumb points in direction of force. This works for current or positive charge. And you might ask, why positive charge? Why not negative charge? Because the equation is Q times V times B. If the charge is negative, then you have negative in that direction, which means it points the opposite direction for a negative charge. So using that right-hand rule, I can take my right hand. Remember, it must be your right hand. If you do it with your left hand, you'll get the opposite answer. And I'm going to point my index finger in the direction of the current, so my index finger is going to point that direction. Then I orient my hand, keeping my index finger pointing that way, make my fingers so they're 90 degrees, and orient my hand so my fingers point the direction of the magnetic field, which is up. And then my thumb tells me that the force is coming out toward you. Now, I could have looked at the charge. If it was a positive charge, I would have had exactly the same thing. But what's really happening in a wire? In a wire, what's really moving? Electrons. So in a wire, it's really, so I'll write it here in green, what it really is a negative charge that's moving that direction. So if I use my right-hand rule, I'll align my index finger in the direction of the velocity, which is now pointing this direction, orient my hand so my fingers can point in the direction of the magnetic field. My thumb points into the screen, so it's, because it's a negative charge, it's a negative force into the screen, which turns out to be still a positive force out of the screen. So it's the same answer, but you have to be a little more careful if it's a negative charge because of the negative sign there. So our first clicker question, computer needs to be awakened. I've been away so long. Waiting such a long time. Okay, you may go ahead and answer now. A straight wire with a length of 15 centimeters carries a current 4 amps. Wire is oriented perpendicular. That color is perfect. There was the equation for those who didn't have it written down. Rachel and Denford. Okay, we had 3, 1, and 1. Okay, doing the calculation, which of those two equations do I use? The one that's the current and the length, or the one that's the charge and the speed?
Well, I saw length up there.
Okay, I have length and I have current, so I'm going to use this one here. My current is 4 amps. The length is 0.15 meters. Notice you have to pay attention to the units. It's not 15, it's 0.15 to put it in the standard units. And then the magnetic field strength is 0.5 Teslas. I didn't talk about the unit for magnetic field strength. There it is. It's Tesla, named after Nikolai Tesla. So I just multiply these things together, and 4 times 0.15 is 0.6. 0.6 times 0.5, really, is, yes, 0.3. So there was our correct answer. So that's a new thing on this slide, the unit of the magnetic field. We talked about its direction. We didn't talk about its units. There is another common unit that's used for magnetic field strength, and that's the Gauss. But the standard unit, the SI unit, is the Tesla, so that's why we have that. So here is the explanation of the right-hand rule, and you'll notice they have it oriented different than what I did. They're not using the standard orientation, so don't get confused. Only learn one way. And believe me, the way I described it is the universal way. This is a... Oh, wait. No, that is right. I should read carefully. They do have the thumb as F still. I don't know why I misread that. There are people who will do the right-hand rule switched by one finger for each one. That gets you confused. So that is the same. I apologize. Well, like I said, the way I taught you is the standard way. So that is going to standard. So here is just examples of the force. One thing that's very interesting about the magnetic force, it's always perpendicular to both the magnetic field and the velocity or current. So that means if I have a charged particle moving in a magnetic field, since the force is perpendicular to its velocity, it does cause an acceleration because Newton's second law says that the force always causes an acceleration. But the acceleration is perpendicular to velocity. Do you remember what we called an acceleration perpendicular to velocity? No? A centripetal acceleration, because it makes things go in circles. Now, you also have the words tangential and radial. So you could also say it's a radial acceleration. But the key is, it'll make things do circles, because the force is always going to be perpendicular to the velocity. Now here's just a picture showing what we talked about, how a loop makes a stronger magnetic field, because each piece of the loop, so here on the right side you're seeing the magnetic field created by current that's going away from you. On the left side you see magnetic field created by current coming toward you, and both of those are making magnetic field in the center that's going up. So it's adding together, and if I make a second loop, I'm just going to add and double my magnetic field. Third loop, add that again. So the more loops you have, the stronger the magnetic field you're going to make. Hence why with this device, I have a huge number of loops to make a much stronger magnetic field. And then I have the iron inside to then multiply again. And that's just saying it behaves like a magnet. Well, yeah. That explains essentially how we were able to make our electric motors work. Because we had loops, coils, we had current going through those coils, and that current then was making a magnetic field, so it was like we had a magnet that was able to rotate and a permanent magnet, and so the magnet would have a torque to make it align. And then what did we do when we had them aligned? We turned it off. For our homemade ones, we just turned it off. And so it's rotating, it gets here, and then it turns off, and so it freewheels for a half cycle, and then we turn it back on, and it pulls it around again. So here we're going to have some pictures of how we make an electric motor. First, making a rectangular coil versus a circular coil. It has the same outcome, but the rectangular coil is easier to explain. Because with the rectangular coil, you have a straight wire, and you can use that equation, force is equal to ILB to find the strength of the force on this wire, and on this wire, and on the two end wires. Now notice this end wire, because the current is going, it's hard to tell in these pictures, but the current is going at an angle that is upward here. Rotate your hand so your fingers can point in the direction of the magnetic field. And on this one here, okay, got to be like this. The thumb points like that. And so the force is actually trying to stretch the loop. That's not going to make it rotate. It's not going to give you a torque, because the force has to be perpendicular to the radius, and that's not perpendicular to the radius. The radius for a loop would be going from here to, somewhere. Well, that's parallel. Over here, that's perpendicular, partially perpendicular. Well, right, because your R is coming up at an angle and the force is going vertical. But it's partially perpendicular, so it makes a torque. So these two forces 3 and 4 make a torque. Forces 1 and 2 don't make a torque. But notice force 3 and force 4, they're both going to try to make it rotate the same direction. And so it's going to have a torque to make it rotate. This is a simple device. It's a step before actually showing a picture of a motor, because it's the same thing as a motor, except instead of doing rotations, you just have a spring and you put current through the wires and it creates a torque, and it rotates until the torque is balanced by the torque of the spring. And so this is used to measure how big the current is. Because if you put more current through, then you're making the magnetic field from that loop bigger, or making the force, the forces that make the torques bigger. And so you get a bigger torque when you put more current through the wire. And that bigger torque means that the spring is going to stretch more until you balance the torque. And so with this system, the needle actually moves with an angle proportional to the current. And so this is a simple device, I believe it's called a galvanometer here, to measure the current that flows through a wire, just by essentially making a motor, but making it so it can't rotate. This should look real familiar. This looks like the ones that were made for us, except this only has one loop, whereas the pre-made ones had 3 loops. You see it has the split ring here. The pre-made one that you worked with had 3 wires coming off of that, 3 pieces. We call it a split commutator. right there. The ones you used had 3 because it would turn this loop on, and then it would turn this one on, and then this one on. And so you were always using 2 of those 3, and one was being omitted for that. Why would it do that? To make it more efficient. So it always was getting close to maximum torque from one of them. But that should be very familiar. You've worked with it. Any questions about the motors? Because I feel like just going past them because we've already studied them, but if you have questions, I need to answer those. Okay. And we've already talked about this. Let's just move past it. And that's why Rachel says it's hard to take notes. Because I talk about things before we see pictures of them on the slide, and then I say, we already talked about that. Like this. Getting on to transformers. Everybody knows what a transformer is. It's more than meets the eye, right? It's not a robot in disguise, though. A transformer, as we use in electricity, is a device that uses 2 coils that are coupled together. So we have one that's called the primary coil. And so you have electric current that comes and goes through that primary coil. And then we have a second coil that's called the secondary coil. And there's no electrical connection between those 2 coils. But if there's no electrical connection, how can they interact? Well, what we do with this is we add one more piece, something like a piece of iron that goes like this. Now, what have we been talking about the effects of iron, such as why I put it in here? Right. When you put a magnetic field on this iron, the magnetic domains reorient to match that magnetic field and make a much stronger magnetic field. If I have wire that forms a closed loop, I will have the magnetic field from the wire cause the other parts to also realign. So what it does is it keeps the magnetic field almost entirely inside of this loop. So the magnetic field is staying inside of this loop. So the magnetic field that I create on the primary, the black coil, then is also going through the red coil. And we saw from the demonstration here that if I have a changing magnetic field going through that coil, well, I said changing. We didn't actually know it was change. We just knew that that magnetic field created a current in the second ring. Now we're going to learn more that it has to be a changing magnetic field. But when I have a changing magnetic field through the second one, it will induce a current in the second one. So a transformer is going to allow us to have current through the primary coil create a current through the secondary coil. Now let's hope that I have this, there we go. Have this in the right order. Here is a picture showing using a transformer. You have a battery on one side and a galvanometer on the other. Why did I say uh-oh for the battery? Because if you connect the battery, you know what's going to happen here? You're going to have a momentary swing on the galvanometer. The galvanometer is the device that we had drawn before with basically like a motor that doesn't move. You're going to have a momentary swing, but then it's going to come back. And then when you remove the magnet, you'll have a momentary swing. So this is a transformer, plain and true. You don't ever use them with batteries. You don't use them with batteries because you only have a reaction when you connect and when you disconnect, and not while the current is continuously flowing. So Faraday was studying this, and he came up with a law to describe what's going on. First of all, he said it's the changing magnetic field that is key. That you only induce a current, he wrote here, or I wrote here, you only create an electric field in the wire if you have a changing magnetic field. And since the magnetic field depends on the current, a changing current on one side creates a changing magnetic field, and that's what you need to induce something on the other side. So some examples of changing. We have to start by saying, how are we going to measure the magnetic field that's causing my secondary coil to have a signal? And we have this thing called flux. Flux is really a measurement of how much field goes through a surface. And so in the picture here that's labeled, it's not labeled. The picture here labeled A, the magnetic field goes straight through the coil's face. That's the most magnetic field you can get through that coil. If you rotate the coil here, none of the magnetic field is going through the face of the coil. And so here the flux, which has a symbol of capital Phi, is 0 because no magnetic field is going through. The picture on the left, the flux is the magnetic field strength times the area of the coil. So this flux, it has units that are really important. Magnetic flux is magnetic field times area. So the units would be Teslas times meters squared, which we call Webers. Very, very vital units. Even though it has an at the end, and it has one B. Nothing in life is perfect. So we measure that magnetic flux, and Faraday says that if the magnetic flux changes, then you're going to induce a voltage. Oh, cannot use green on this blue background. So the induced voltage is the rate at which that magnetic flux is changing. So that would be equal to the change in magnetic field times area that it goes through over, and really should have a delta there for a change in time. What if you had 2 loops instead of 1 loop? That's if I have a wire that comes and makes 2 loops instead of just coming and making 1 loop. What's that going to do to your flux? Yeah, it's going to increase it. It's going to double it because your magnetic field is going through 2 loops now instead of 1 loop. And so we put N here outside for the number of coils, each coil having the flux of BA. It's called electromagnetic inductance because you are inducing a voltage. That is, you're creating, from the magnetic field, you're creating a voltage that flows in your wires. I am flying. Okay, this graph is showing magnetic flux on the vertical axis. So what we're saying is I have a loop, and the magnetic flux going through that loop is shown in this graph. And the question to you is, where does the induced voltage have its largest magnitude? Your options are, I'm writing in white. A is from here to here. B is right there. C is from here to here. D is right there. And then E is from there to there. Okay, everyone's answered. We have 10301. All right, this is non-good, non-good. Actually, for those of you who know Bill and Ted's Excellent Adventure, non-good actually means good. So this is non-good. Or, yes. Our induced voltage had that equation V induced. We use this symbol script E for EMF, electromotive force, is equal to N change in flux over change in time. The flux was the beat A, but here we just had flux. So what is the key for getting the maximum induced voltage? The most change in flux per time. Now, if I have a graph that has flux on one axis and time on the other, how do I get change in flux per time from that graph? Remember, the vertical is the change in flux here. The horizontal is the change in time. What value is change in flux over change in time? The slope. So another way of asking this question, which would have taken away having to know physics and would have just made a math question, would be to ask, where do we have the steepest slope? Where do we have the steepest slope? From 0 to 1 second, because it goes up, whatever this amount is. Okay, white isn't going to work. In 1 second. It goes down that same flux in 2 seconds, so that's half the flux for E. What about what's going on at C? You have what? You have the slope is 0, so the V induced is equal to 0. During that period. You have to have the change in flux. That's why the battery doesn't work with the transformer. Because with the battery, you're putting out a constant voltage or a constant current, and so your coil is going to have a constant magnetic field, producing a constant magnetic flux and no changes. I have one more demonstration that I forgot to grab, but I've got that back door open. I'm going to end with this demonstration. This demonstration illustrates essentially the same thing as that ring tosser, but it illustrates Lenz's law as well. Lenz's law is a law that tells us about the direction of the induced field that was occurring with that ring tosser. So in this little device, this is made again of brass, so it's non-magnetic. I don't have any actual magnets up here, so I can't. Oh wait, one of these is a magnet. No sticky, no sticky. These two stick together, so you know one's a magnet. Take these. Oh, this is not magnetic material. This is magnetic material. That one sticks, this one doesn't. So we can easily see magnet, no magnet. Now I need another volunteer to come and have steady hands. I do need a volunteer. I cannot do this by myself. Thank you, Rachel. I mean, I know Denford would have come again, but you don't want to pick on the same person every time. Okay, one of two jobs. Either hold this so it hangs vertically, or drop this in the center.
I'll hold it.
Okay. So it's got to hang vertically, and I have to drop it in the center. If I don't drop it in the center, you'll hear it humming as it rolls around the inside. And what we're just looking at is how long it takes to fall through. Clearly that was not dropped in the center. That wasn't either. Dang it. It's hard to do this. It works if the person can drop right. There we go. Fell right through. Now I take the magnet and do the same thing. Remember, we're timing how long it takes to go through here. It wasn't rubbing on the sides, right? You didn't hear the rattling stuff. It just went nice and smoothly through there. But it takes a really long time. Why? Well, we call this eddy currents. As the magnet is falling, what's happening to the magnetic flux in the region of the pipe below the magnet? It's getting stronger, right? Because the magnetic field is increasing in strength. And so the magnetic field is increasing, the magnetic flux is increasing. Faraday's law says that that's going to induce a current. And Lenz's law says that current is going to make a magnetic field that opposes the change. So if the magnetic field was pointing down and getting stronger, then Lenz's law says the current that's flowing in circles in this tube below is going to make a magnetic field that's opposing the magnetic field. And if I have north points north, what do? They repel. And so the material below the falling magnet is pushing the magnet up to slow it down. Now, above the magnet, as the magnet moves away, the magnetic field is getting weaker. Lenz's law says the induced current is going to flow in the direction that's pointing the same if the magnetic field is getting weaker. And so then I have two magnetic fields that are both pointing the same direction, north pointing to south, they attract. So the portion above the magnet is trying to pull it up. So below is pushing up, above is pushing up. They're both pushing up with a force that's proportional to the speed. And so the speed slows down until you get to the point where the force of the eddy currents, the magnetic force is pushing up, is equal to the weight of the object. And this is very practical in things like roller coasters. You've probably been, or at least seen, roller coasters where they take you up 50 stories or whatever, and then they drop you straight back down. How many people have been on one of those? Okay, it does kind of scare the poo out of you. What if the power went off just after your release, the power goes out? No, because they have essentially this set up on that. They have little vanes that stick out from the tower and magnets that are on the sides of your car that the vanes will then go between the magnets. And as the magnets go through there, it'll create currents below that repel the magnets and currents above that attract them. So it will slow it down even if there's no power. So you will slow down quite a bit, and then you get to the bottom and they have springs. You would be fine if the power went out, which is a good thing, right? All right, have a great day. Enjoy the alumni weekend. I'm sorry I went twice as long with that as I anticipated.